Math 2414, Calculus 2. Calculus 1 review. Derivative rules, part 3. Before we complete these derivative rules, which you may already know, which you should already know, upon further reflection, I think that I'm actually going to have 5 parts to these derivative rules. I was going to do trig functions and inverse trig functions in one video, but either I can't do them justice or the video would be way too long. So this video will be trig functions, the next video will be inverse trig functions, and then the 5th video might be something some of you are not familiar with, hyperbolic trig functions. They're not really that difficult, they're just a little bit different. But anyway, some of these rules we're going to derive, some of them I'm just going to give you because the derivation of them goes really in depth into some Calculus 1 shenanigans, which I don't want to invest time going over right now. But if you're curious about the first rule or two, I highly recommend reviewing Calculus 1 to see the genesis of these rules. Let's start with number 11. If f of x equals sine of x, then f prime of x is equal. Most of you already know that the derivative of sine is cosine. And by the way, I expect you to know things like sine is opposite over hypotenuse and cosine is adjacent over hypotenuse and all that jazz. I expect you to know things about 30 degrees, 45 degrees, and 60 degrees. I expect you to know things like Pythagorean identities, quotient identities, and reciprocal identities. And if you don't know what I'm talking about, get with me and I'll hook you up with some material to review a lot of the trigonometry that you've got to know in this class, early and often. But I digress. The derivative of sine is cosine. Number 12, if f of x equals cosine of x, then f prime of x is equal to negative sine of x. The most common mistake people make here is remembering which one is positive and which one is negative. By the time I get to the end of this list, I'll show you a really easy way to remember which derivatives are positive and which derivatives are negative. Number 13, if f of x equals tangent of x, then f prime of x equals. When you go past sine and cosine, people have trouble memorizing some of these rules because they kind of seem random and arbitrary and different than these two rules, which seem pretty easy. They're each other's derivatives, except one of them is negative. So let's actually derive the rule for tangent. Now, how would we do that? Well, the same way we did the derivation of the last derivative rule on the previous video. You take what you don't know and connect it to what you do know. So what do we know about tangent of x? Trigonometrically. Well, there's a quotient identity that says tangent of x is equal to sine of x over cosine of x. This is really easy to prove using opposite over hypotenuse and adjacent over hypotenuse, cleaning it up, and the resulting ratio is opposite over adjacent, which is tangent. But if we start here, why is this better than tangent when it comes to figuring out its derivative, assuming we don't know the derivative of tangent? The answer is, we know everything about how to take this derivative. We have a rule for quotients, we have a rule for sine, we have a rule for cosine. So to derive the rule for tangent, we simply have to rewrite it as sine over cosine and apply all the rules that we already know. So let's do the quotient rule. Derivative of the top times the bottom. The derivative of sine is cosine, times the bottom is another cosine. So on the next line, that'll be cleaned up as cosine squared. Minus the top times the derivative of the bottom. So minus the top, sine of x, times the derivative of the bottom, but the derivative of cosine is negative sine. So not only will we have a sine squared, but we have a product of two negatives, which will be positive. And on the bottom, we take the original denominator and square it. So we'll take cosine and square it. You should know by now that when you raise a trig function to a power, it's customary to put that power directly on the trig function. Just a reminder though, something like cosine squared x literally means cosine of x squared. Oh, and one more FYI about the way I write trig functions. You might be wondering why I put parentheses around all these x's when I wouldn't have to. The answer is real simple. They are trig functions. And more importantly, they are functions, and anytime I write a function, I put parentheses around its argument. It's not wrong to leave the parentheses off here. I just like to be consistent with the way that I write my functions with parentheses around their arguments. Argument being the generic term for what you put into a function. That's the same reason I did natural log of x over here with parentheses around the x. This is a function and this is its input. So it's just a habit of mine to customarily put parentheses around any function's input, whether it's a generic function like f of x or a specific one like natural log of x or sine of x. But let's go back over here. All right, so we've taken the derivative using the quotient rule and the rules for derivatives of sines and cosines, and now it's just a little bit of algebra, a little bit of trigonometry. In the bottom we get cosine squared of x. In the top we have cosine squared of x. The double minus becomes a plus, and then we have sine squared of x. Now, if you're about to cancel these cosine squareds, slap yourself, stop it, don't do that. There are things I expect you to know, like in algebra, what you can and can't cancel in a fraction. If your temptation is to cancel these, you need to do some serious algebra review, because the rule for reducing in a fraction is simple. You can only cancel parts of multiplication problems, because multiplication is the opposite of division. You cannot cancel parts of addition problems. Don't you dare cross these out. I will give you dirty looks, and in my mind, I will throw things at you. So I can't cancel these. But look on the top. We have cosine squared plus sine squared. Do you know what that equals? There's a Pythagorean identity that says sine squared plus cosine squared is equal to 1. So already I've used two versions of trig identities. A quotient identity that says tangent is sine over cosine, and a Pythagorean identity that says cosine squared plus sine squared is equal to 1. And I'm about to use one more. I'm going to use a reciprocal identity. I'll put the square back in a minute, but you should know that 1 over cosine is secant, which means that 1 over cosine squared is secant squared. And that's as simplified as that can get. The derivative of tangent is secant squared. Now, if you knew that it was secant squared, that's great. But if you forgot, this is where it comes from. Now, you don't have to reinvent the wheel every time you take the derivative, but unless you have everything completely memorized, which you probably don't, it's nothing personal, but it's a lot to memorize, it's a good idea to remember where some things come from. And it basically reinforces your skills, so there's no shame in saying, hey, I think I can prove that this is equal to that. All right, I'll go ahead and give you the rest of them without all the song and dance. We could do the same thing for cotangent by writing it as cosine over sine, and at the end it would end up being negative cosecant squared of x. We could find the derivative of secant by writing it as 1 over cosine, doing the quotient rule, or the chain rule if you want to write it as cosine to the negative 1 power. But when it all washes out, the derivative of secant is secant x tangent x. If you'd like to see the proof, just shoot me a message and I'll whip up a quick video. And then the derivative of cosecant is negative cosecant x cotangent x. All right, to wrap up this video, I just want to show you some gimmicks for remembering all of this, even though we can derive all of it one way or another. At the beginning, I mentioned that there's a real easy way to remember when the derivative of a trig function is positive and when the derivative of a trig function is negative. Look at all the ones whose derivatives are positive. Sine, tangent, secant. Now, look at all of them whose derivatives are negative. Let's use, this color looks neat, let's see if it writes. Yeah. Look at all the one whose derivatives are negative. The derivative of cosine, well, that looks like that color, that's not what I wanted. Hold on, folks. I've got a variety of colored markers over here. I'm just trying to mix up the colors some. All right, so whose derivatives are negative? Your derivative, and your derivative. Notice anything about the three trig functions whose derivatives are negative? Cosine, cotangent, cosecant. They are all co-functions. That is actually what they're called, co-functions. And the other functions are not co-functions, just sine, just tangent, just secant. So one way to remember whose derivative is negative is the following statement. A trig function's derivative is negative. A trig function's derivative is negative if and only if it is a cofunction. So when you take the derivative of a function, trig function, if your function starts with co, its derivative is negative, otherwise it's not. So there's an easy way to remember whose derivative is negative and whose derivative is positive. I do want to point out one more interesting relationship between the derivative of each trig function and the derivative of its cofunction. In other words, sine and its cofunction cosine, tangent and its cofunction cotangent, secant and its cofunction cosecant. Let's assume that you have the derivatives of sine, tangent, and secant memorized. In other words, all the positive one. Derivative of sine is cosine, derivative of tangent is secant squared, derivative of secant is secant tangent. To get the derivative of a cofunction, you just take the original function's derivative, change the sign, and change each function to its cofunction. In other words, to go from sine to cosine, change the sign, S-I-G-N, and take the cofunction of cosine. Well, the cofunction of cosine is sine. Or, if the derivative of tangent is secant squared, then the derivative of its cofunction is the negative of the cofunction of the derivative. In other words, derivative of tangent is secant squared, derivative of cotangent is negative, cosecant squared. And the same thing here. I think I just said something incorrectly up there. Or maybe I didn't. If the derivative of secant is secant tangent, then the derivative of its cofunction, cosecant, you stick a negative and take all the cofunctions. Stick a negative, the cofunction of secant is cosecant, the cofunction of tangent is cotangent. It's actually easier to do than I think I'm saying right now. Just take the derivative of the function without co in front of it. Then for the derivative of the function with co in front of it, change the sign, S-I-G-N, and take each of these guys' cofunctions. By the way, I think I said this before, but if the cofunction of sine is cosine, then the cofunction of cosine is sine. It's a two-way deal. All right, so there's your 6 derivative rules. Know them, know them, know them.